All right, guys, I have a few Ask My Instructors that were sent to me over the last day that I wanted to go through. You can tune me out if you want. Some of them won't apply to you, right? Because these were specific questions from different students. I wanted to go over them together just because multiple people were asking the same questions. So, starting out, this was one that got sent to me. Solve for x, and then it asks us to find out what x would be. Now, this is a square root equation. So in order to solve for x, what we need to do is we need to kind of peel away the pieces for x. And so right now, if I want to get x by itself, it's stuck in a parentheses with an exponent. Now, how do I get rid of an exponent? I use a radical. So in order to get rid of the squared, I'm going to square root both sides. Now, here's where it gets that thing that people miss. That would make this x minus 5. There's no squared anymore because we square rooted it. But on the other side of this equation, the square root of 4 is 2, just 2, right? Square root of 4 is 2. But when we solve an equation using the square root method, it's actually plus 4 minus 2. There's more than one possible answer. Now when we go ahead and solve it, it's like solving two separate equations. In other words, we're going to solve this by adding 5 to both sides. And I get x equals 5 plus or minus 2. That is to say, x is either 7 or 3. So there's actually two possible answers. Now, if we go back and think about this for a second, if I were to plug in the 7 for x, I would get 7 minus 5 is 2, and I'd square it, and I'd get 4. That would work. If I plug in the 3 for x, well, I get 3 minus 5 is negative 2. And if I square it, the negative cancels out. And so that works too. They both work. And so make sure when you type them in, you put a comma between them. Just be aware when you use the square root method, you need to remember the plus or minus. Next, one of my most hated questions for the year is the astronaut problem. This is an astronaut who weighs 250 pounds at sea level. And it actually tells us the formula we're going to want to use, we need to create. It tells us a few important details. It says the W equals FD of an object varies inversely as the square of its distance. So in order to write that equation, we go ahead and take the W or FD, either one. It says they're the same. Varies means we're going to write equals K. And then it says inversely. So when it says inversely, we're going to write divides. And we're going to put it on the bottom. Instead of just writing an x, it says the square of the distance. So we're going to say d squared. Now, it might be tempting to go ahead and plug that in right there. But if you do that, it'll count it wrong because that's not what they're looking for. They want you to find the equation and find out what the k is in this equation. So luckily, that's something we can do because we have that 250 pounds. That's our W. And we have a 4, that's our D. And so we can plug those in, and we get 250 equals K divided by 4 squared. And we can go ahead and plug that in, and we get 4 squared is 16, and divide that both sides, and so we get 250 divided by 16 equals K. What is 250 divided by 15? Anybody got a calculator? I'm going to use my phone because I didn't bring a calculator with me. What is it? 16 point something? 16.6. All right, so then that means what I'm going to write is that 16 point, what did you say, 6 repeating? I'm going to write 6, 7. Over d squared. So my formula that I'm going to write in here is just like that. The follow-up question, it says, how much would an astronaut weigh at 1,000 miles? And so I go, oh, good, 1,000. So I'm just going to type in the 1 for D. But here's the catch. Every part of this question has a catch. The catch here is that the 1,000 miles above Earth's surface is not what I'm going to plug in because this is measured from the center of the Earth. So we need to combine the numbers we had in the first part and the second part where it said sea level, in other words, Earth's surface. is 4,000 miles from its center. So if we're 1,000 miles above that, how far are we from the center? We're actually going to have d equals 4 plus 1 is 5. So we're actually going to plug in 5 instead of plugging in the 1 that they give us. So every step of this problem has a trick. But once we plug in 5, we should be able to get an answer. Now, I wanted to know how long it would take before anybody called me out, but I just can't wait anymore. I've made a mistake early on, and nobody stopped me. You guys went with me. What's the mistake? Oh, I did. What's the mistake? For those of you that have done this problem before, you'll probably be like, you know what, I got a number bigger than 16. I got a bigger number. What's the deal? No. So I want you to notice when I went ahead and plugged it in, and I'm going to kind of highlight it in here in green so you can see this looks great. This looks great right here. But when I went to solve for k, I tried to get k by itself, and I said, oh, well, I'm going to move that 4 squared, that's 16, and I'm going to divide it on both sides. But since the 4 squared is on the bottom, I shouldn't have divided. I should have multiplied, right? If I want to take that 4 squared and move to the other side, I should be multiplying 16 times 250. So k in this case is not the 16.67 because I wasn't supposed to divide. K ends up being the 250 times the 16. Remember that when you have that, we're trying to get the k by itself, we need to do the opposite. Which means my k is not 16.67, my k is 4,000. So now when I plug in my d squared, I plug in my 25 for my second one, I'm going to end up getting that 160. Okay. The next part says, at what distance from the center of the Earth would the astronaut weigh 1 pound? Now, I'm looking for the d. It's telling me the weight is 1 pound. Which means I need to come up with the formula here. Now, back to this formula, that means the 1 is going to go right here. Now, when I deal with fractions, a 1 as a fraction means it's got the same number on the top and bottom. Same number on top and bottom. So that means that d squared, what's d squared? That's 4,000, right? Now, I could multiply by d squared on both sides and get 1d squared equals 4,000. So how do I figure out if d squared equals 4,000? There might have been a reason I did the problems in the order I did them. How do I get rid of that exponent? How do I get rid of that squared? I square root both of them. And the square root of 4,000, I'm going to type it in my calculator. I never know whether I'm supposed to do the square root button first or last. And I got like 63.24 miles. Here's the catch. There's a catch in every one of these questions. That's still the wrong answer. Because d is not in miles. It's in thousands of miles. So when I solve that and I say, oh, well, d is 63.2455, so I'm going to say 246. That's not how many miles it is because that's supposed to be thousands of miles. So I need to multiply that by 1,000. So it's actually 63,246 miles. Just for funsies, I am recording this, and so I'll post this in Canvas for you, okay? I am recording this right now, just so that you can have it. Estimate the amount an astronaut would weigh on the surface of the moon. Now, the surface of the moon, it tells us, is about 239,000. It doesn't really matter if we add the 4,000 like we did in the second part because 239 is such a big number. If we plug in 239, we end up getting a very, very small number. In fact, we get 0.07 pounds, which is very light. I went to the gym and worked out this morning, and that was how much I was lifting. I was lifting 0.07 pounds. But that's like crazy light. And so the follow-up question to this one says, hey, has model breakdown occurred? Has model breakdown occurred? Yeah, that doesn't really make sense as an answer, because if they were that light, I know I've seen like videos of when they staged the moon landing and they are like kind of floating, but if they weighed 0.07 pounds, like they could jump all the way off the moon. Like just like if you weighed that much, you basically weigh nothing. So this didn't really make sense. And if you had a lighter astronaut, you would end up with smaller numbers. Let's look at another one of those ones that is very similar because it's crazy, but this one, it tells us a little bit of our information. The intensity in watts per square meter, so it's got watts over meter squared, of a television signal varies inversely as the square of the distance. Now, this is kind of a gimme here in the setup because since they tell me the units, I already know that I'm going to take the watts and divide by the meters squared. And so it tells me that the intensity of a television signal is 40 watts over meter squared, and the distance is at 2.6 kilometers. But since it doesn't say kilometers squared, it says meters, I need to recognize that 2.6 kilometers is actually 2,600 meters. So this one, when we set up our equation, don't forget we need to switch the 2.6 kilometers into meters. After we square that, we're going to remember to multiply on both sides. This one, we're looking at inflation a little bit. It's saying it cost $6 to fill a gas tank in 1970, but inflation is proportional. So I'm going to use a proportion. To fill a gas tank, the entire gas tank would only cost $6 in 1970. And that's partly because the price of gas was $0.36 per gallon, which is insane. So now the question says, how much would it have cost in 1960? Okay, so I want to know how much it would have cost in 1960. Well, in order to do that on a set of proportion, I need to recognize that gas was even cheaper back then. It was 0.31. I just got that right there. And then I can cross multiply and divide. I can actually just solve this proportion just like that. And so I should get a number. I'm going to try it. I'm going to do the 0.31 times 6. And then I'm going to divide that by 0.36. And I got $5.17. And I'm going to do a little gut check. Does that kind of make sense? Yes, that kind of makes sense, because if it was $6 in 1970 and it was a little bit cheaper, yeah, that makes sense. Like if I got 50, I'd say that doesn't make sense. Next, we have a CPI question about inflation rate. Now, this is looking at inflation, and I'm going to set it up 1996 to 1997. We're just looking for that 1 year difference. So in order to do that, we want to know how much did it change. So we're going to take the CPI in 1997, which is 160.5, and we're going to subtract what it was the year before, 156.9. If we subtract those two, it tells us how much it changed, right? How much it go up. So I'd be like, oh, look, I'm done. It's 3.6. But here's the catch. If we're talking about it as a percent, that means we need to know what are we dividing by? What goes on the bottom? And what goes on the bottom is what it started at, 1996. It started at 156.9. So we're going to take that 3.6 and we're going to divide it by the 156.9. And if we do that, we get 0.0229. But that's not the answer. The kind of hint here is that it says round to one decimal place. And if you round to one decimal place, you get 0. Okay? Because as a percent, remember that we need to move the decimal 2 places. So we're going to move it 2 places. And so it's 2.29, or for our answer, 2.3%. Here's another CPI one, except I'm actually going to do this one, not because it's not asking me what the inflation rate is. It wants to know if I changed when I bought something, how much would it have cost? So I'm going to do this like a proportion. So the first thing I'm going to do is I'm going to say, suppose you needed 38,000. So I'm just writing down the number it gives me to maintain a particular standard of living in 1980. How much would you need in 2000 to have the same standard of living? So I'm saying if this is 1980, what would 38,000 be, the equivalent be in 2000? Okay, so in order to do that, since I'm looking for this number, I'm going to use this CPI table to find it. The first thing I'm going to do is I'm going to find the CPI for 1980, 82.4, and I'm going to find the CPI for 2000, 172.2. And guess what I have? I've got a proportion I can cross multiply and divide. I'm going to try that now. I'm going to use my calculator and I'm going to multiply diagonally 38,000 . And I got 79,41262. And it says round to the nearest dollar, so I'm just going to take that up a notch just to. So 38,000 in 1980, if you wanted to live the same kind of life, you'd need to be making 79,000 in the year 2000. That is all of the Ask My Instructors that I was shared. I am recording this. I'm going to go ahead and stop the